Okay, good morning everyone. Yeah, we'll start in about a minute, so if you're just coming in, settle down and we'll get started. Thanks. Okay. Right then. So we are just over halfway through the first part of the course. Things are, well, I wouldn't say going to get a lot more complicated, but things are coming together. Things are starting, we're going to start to build on some of the basic principles that we've been introducing. And one of the things about fluid mechanics, as is true of physics in general, is of course that all the principles are linked and all the things that we talk about come together at different times in different examples and different circumstances. So always the challenge is taking the concept and applying it in practice. And this is another example of that we're going to look at today. So a reminder, we've got tutorials next Friday. The tutorial sheet 2 is available. Please have a go at that. It's going to be some similar types of questions to what you're going to be asked to do in the coursework, which is going to be issued in around a week's time. Remember, the coursework's worth 10%. And these are your groupings for the tutorial. Okay, today's lecture notes are here. And we're going to look at forces on a submerged plane today. So up until now, we've been looking at pressures in a hydrostatic fluid, but we haven't necessarily translated the pressures back to a force. And that's what is going to be the topic of today. We won't cover all of it today. You'll see in the notes that there's a certain amount of pre-read that's required, and the condensed notes themselves start to get quite complicated. So please have a look through that. It's important that you are able to follow the basics. You won't be required to recall derivations by hand, but in an exam. But you will be required to necessarily to use equations that you might be given, right? So you need to understand what the equations mean and what's actually going on in those in that topic. Okay. So because it's new to some of you, I introduced asynchronous video at the beginning of the week, which covers second moment of area. I think we ascertained that was a relatively new concept to some of you, and so hopefully you've had a chance to look through that before today. I'm going to go through it again quickly, but probably not in as much detail as I do in that video. So if there are additional questions that are arising, I'd recommend that you see that video first if you haven't already done so. Then we're going to look at forces on a submerged planes, so a horizontal plane and a vertical plane. Horizontal plane is relatively straightforward, so vertical plane is a bit more involved. And then we're going to move to the general case. We're not going to probably go into too much detail for the general case, where it can be inclined at any angle and it can have any shape. But we're going to hopefully in today's lecture cover the tools that you need to use in order to address that problem. And then I'm going to point you towards some worked examples in order to demonstrate that. Okay. So forces on a submerged surface arise because of a pressure, and the pressure is a force per unit area. So we introduced this right at the beginning, and then up until now we've been talking in terms of pressures. Remember that the force is going to be acting normal to the surface because the pressure is always the component which is bombarding the surface, is acting on the surface. And in general, if we want to calculate the force, we have to work out the variation of the pressure around the unit area. So in the analysis today, we're going to start to do integration on an area, now first in 1D and then in 2D. And we're going to show that we need tools like the first moment of area, the center of gravity, the centroid, and the second moment of area in order to properly represent and calculate arbitrarily complex shapes. And you can see the classic examples we use in hydrostatics are dams, tanks, submarines, gates. They're generally not always simple shapes. You can have any range of shape, any range of cross-section, and it's not enough to be able to do this just on a simple vertical surface or a horizontal surface. We need to be able to generalize that in engineering. Okay. So these next, I think, 3 slides are the content that I gave you previously. We're going to go through them again quickly and give you a chance to ask any questions. So you all will have heard of center of gravity, centroids, and you all will have basically understood, I'm sure, how to calculate them in 1D first and then in 2D. But probably you might not have seen it written in this more formal way, where you're essentially taking, you're doing an integration of an arbitrarily defined shape in grey between its minimum extent and its maximum extent, and you're calculating its, if you like, its moment from the axis of reference, or here, the y-axis, and calculating how much of its mass is located at that location away from that axis. And if you calculate the sum of that, and then you divide by the total, then you get the resultant, the average location of the mass, which is the average position of the mass in that coordinate. And that's the center of mass, the centroid in that coordinate. And when you have a 1D geometry, you only need to do it in one direction. When you have 2D or 3D, you need to do it in every direction. And you sum the incremental mass, a distance away from a fixed origin, and then you average it, and you're left with a coordinate for the centroid, which is represented by this cross in the middle. Okay. Any questions about that concept? Yes, please. Right, so how do we effectively integrate dA? Yeah, so don't worry too much about that for now. We would use a substitution of, we would say that the area is an x increment versus a y increment, an x increment times a y increment, and so we would have maybe y times dx, or x times dy, according to the direction that we're integrating over. And that would allow us to integrate either against x or against y. And there's an example of that coming up later in today's lecture. So for now, just read it, if you like, as the integral over the area. But it's a fair point. Okay. Yeah, please. After the integration, so the question is, after the integration, are you essentially getting a volume? So interesting, you're getting something that has the units of a volume, but then you're dividing that by a reference, the total area, to get something that has the units of a length. It's not a volume that has any physical significance, but it has the units of a volume. Sorry, could you repeat that? So I think the question is, would you be able to use polar coordinates if, yes, yeah, that's a very good point. So depending on the shape that you're looking at and the application, polar coordinates can often be a preferred coordinate system. If you're looking at, let's say, the distribution of mass on the surface of a planet, then it would make a lot of sense to use polar coordinates or even spherical coordinates. Yeah, so basically this applies to any coordinate system, but for now it's probably most clear if we consider this in a rectangle. So, okay, we've defined the center of gravity in a certain way. We then use that same framework to define the center of area. And the only difference is that instead of having the moment, the distance to that particular part of the mass on its own, we have that distance squared. And there's various reasons why we do that, but for now just consider it that it's the distance squared to the incremental part of the shape, incremental area of the shape. And we consider this for, again, for a rectangular plate. We have a strip width. This is where, for instance, where we can represent the incremental area as an incremental change in y times a fixed width b. So if we're going in the vertical direction, the strip will always have a width b, but it will only have an incremental change in y. So if we're going to integrate against y, we can make that substitution, and then the b goes outside of the integral because it's constant. And then we can integrate y squared to be y cubed divided by 3. So for now, this is a way to represent the square of the distance from a reference axis to an incremental area, and then we sum it between the limits of that shape against that axis, so between y min and y max. And so again, if perhaps that is entirely new to you, I go through that in a little bit more length in the video that I posted on Monday. Please have a look at that if it is new. This is something you're going to see again and again in engineering. It's used for a range of things. Used for instance, looking at the beam bending properties and how if you change the cross-section of a beam in structures, it will resist certain loads applied to the beam. And it's used for various other things as well in dynamics. So for now, we will make a note that this is our expression for the second moment of area of a rectangle around one side of its shape. So any questions? I'm not going to go, I don't want to spend too long on this, but if there are any questions that I can help at this stage. Yes? Would it be a double integral? Right. So, I mean, the short answer is it's not, but there's a longer answer to explain why, and it's basically because we're considering one axis at a time. Okay. The longer answer is that you can have a second moment of area in any combination of directions. So you can actually have the change. At the moment, we're looking at the change in mass distributed in the vertical direction with respect to the horizontal plane. And so that's, if you like, it's inertia around that reference axis. We could also look at that distribution around that axis, and we could look at that distribution around both axes as well. And in 3D, you have more combinations. So you do have, if you like, a tensor or a vector form of this quantity, and then you do have a double integral. But for now, we're just looking at in one direction to make it a bit more simple. But if you want to see that in a bit more detail, it covers it a bit in the textbook. Okay, good. Right. So I guess something that to put your mind at rest, perhaps you're not expected to remember these things off by heart, but you will probably start to become familiar with some of them because you'll use them so frequently. And again, the most important thing is to know what do they represent. You would be given reference quantities in an exam. If you were asked to do a coursework or a report for industry, then you would refer to a textbook that has all the reference types of second moment of area for different shapes. In certain cases where you have an arbitrary shape, you have to use some kind of a script or a program to calculate your own moment of area. If it's not one of these regular shapes, you have to do that by hand. But again, that would be done using a computer software. Okay, so what we're going to look at now is starting to think about how do these pressures translate to forces. And this is a question I posted earlier on Piazza. I think I had Piazza working in the end. It wasn't cooperating for a while. But yeah, okay. So I think there's been 1 or 2 comments. Feel free to post some more. The question is, you have these 2 tanks filled to the same height with the same liquid, and the second tank has a cross-sectional area A at the base, which is twice that of the first tank. So what can you say about the average force that's acting on the base of each tank? So what are the thoughts? What are your thoughts? Same tanks. The one's just got twice the base area of the other. Same liquid filled to the same height. Yeah? The average force is the same, okay. Any other thoughts? Yep. The one and this one is twice. Okay. Do you want to explain why? Give it a go. Yep, exactly right. So, gentleman said the height is the same in both cases. So the pressure felt at the base of the tank is the same, because it starts at atmospheric pressure, then it goes down the same distance in the same fluid. When it gets to the bottom, it has the same pressure. And now a pressure is a force per unit area. So a force is a pressure times an area. If the area is twice, then the force will be twice. Okay, yeah? Do you have a question? No? Okay. Okay, so yeah, this is our first attempt at introducing or computing a force at the bottom of on a submerged surface. And we're going to go through this in a bit more detail here. So we know from last week that the pressure difference is equal to the height difference times by the density and the gravity, or the specific weight. To make things a bit easier for this analysis, we generally then introduce a variable h, which is our distance vertically, but in the opposite coordinate direction to z. So h is simply minus z. I don't really like having to introduce another variable for a very similar quantity, but the course book does this, and it's quite common to have this. So it's important that you're aware of when this is used. So we're going from our pressure is changing in the vertical up direction to now going in the vertical down direction. H. But the advantage is that it's then positive. So the increase of pressure is then in the same direction as the coordinate h. Okay, so consider then this force acting on the bottom. We know the pressure variation through the fluid. We know that if you go a certain height down, you get a certain pressure, which is going to be equal to your atmospheric pressure times the specific weight times that height. Remember that the pressure is going to be the same at the same distance, so it's going to be constant across that base. And so the force that is felt is going to be obtained by using the area of that base. Pressure is the force divided by an area. So if we want the force, we have to times that by the pressure, which is the constant across the base. Okay, so any questions about that? So that's, if you like, our first result. Our first result, which is saying how do we calculate the average force on a submerged horizontal plane. It makes sense to start with this one, because with what we've learned about hydrostatic fluids, they have the same pressure in a horizontal plane. So this is the easier one. What happens when we start to consider a vertical plane or a general arbitrary alignment is that, of course, we have to consider that the force is changing along the vertical direction. And this is where it gets a little bit more involved. Okay, so how does it look when we start to go down of the side of the container. Okay? So you have to bear with me with the next few slides. There's a fair amount of analysis and development, but if you get stuck, we can go into a bit more detail and ask questions as we go. So what we're going to do now is look at how the force is changing down the side, and the force is directly proportional to the pressure. So the force is going to be increasing as you go, and the pressure is going to be increasing as you go. So it helps, for the purpose of analysis, to split up the side wall into some vertical small chunks, right? So we've represented that in the picture. These are small elements of the wall. And in theory, if we know the pressure at each of those chunks, and we assume that it's constant over each of those chunks, then we can work out the average, right? We just sum them up and divide by the number of chunks, and we get the average. And that will give us our average force and our average pressure. And this is going to act at this average is going to act at the center of the gravity, the centroid. You don't need to take my word for that. We're going to prove that in one of the next slides. We're going to show that for this particular case of a vertical plane, it's always going to act at the halfway point. And the other thing that we're going to prove is that although the force can be calculated by the halfway point, the center of pressure, if you like, the average of the force of the pressure, so the average of the effect of the pressure, isn't at that location. It's 2/3 of the way down. Okay? And the only way that we can compute this is by looking at the moments of the forces. Okay, so in this case, we've got an increasing force acting on each section of wall. Each time, the force F acts a distance y from the surface. And a moment taken from the top of the tank is the sum of that distance times that force. And we need to sum the moments in order to work out, if you like, where the average moment is. And the average moment is going to be the center of pressure. So we take our elements, we times the depth by the force, all the way down, and then the sum of all of those is going to be the resultant force times by the moment arm, which is the center of pressure, HCP. And again, we're going to prove that in a few slides' time that for a vertical surface, it's 2/3 of the height down from the surface of the fluid. The interesting thing, that might not be immediately obvious, is the forces are the same. It's just that in the first step, you're calculating the average force. In the second step, you're calculating where it acts. Okay, so this is the important concepts that are going to that form the basis of what we're going to look at in the next few slides. So if anyone's got any questions on this, let's discuss this for a bit now. It might be not immediately obvious, but if you think about it, and if I can, I'll try and find some video demonstrations of this. As you immerse a surface in a fluid, if you imagine the side of a tank, the force just under the surface of the water acting on the side is going to be a lot less than the force at the bottom because of the weight of the fluid above it. So it makes sense that the cumulative force is going to be below the halfway line because it's the sum of all the forces. Yes? How do we find the resultant? So the fortunate thing, or if you like, the easy way to think about it is the resultant is simply the pressure is the average force. So it's the pressure at the halfway point of the tank. Because the individual forces are purely a function of their height below the surface. But remember that the sum, the integral of those forces, times by the sum of that force times by its moment is going to result in a moment which is a distance which is below that location. Okay, let's go through this in a little bit more detail. Right, so we've we're okay. We accept that the pressure is changing linearly in this constant density fluid from the surface down to the bottom. And we're going to split it up into incremental chunks so that we can do some analysis, and the analysis is integration. So we need to do integration. And our pressure is the integral of our force is the integral of our pressure times by unit area. And we're going to use the expression that we had on the previous or an earlier slide, that the pressure is the atmospheric pressure times the specific weight, plus the specific weight times the height below the surface. A few things we can do to simplify this expression. Right, the first thing, the special case that this is a container or a dam or a situation where you have a fluid on one side and nothing on the other, or just air on the other, is that we can simplify the balance of the forces. So you can see in this diagram here, we have three pressure variations. We have the pressure due to atmospheric pressure acting on both sides, because there is going to be a component of atmospheric pressure. And we have the pressure due to the increase in depth through the fluid. And because we're looking specifically at the force acting on the resultant force acting on this wall, we can simplify it by taking out the atmospheric pressure, so it's equal and opposite. So another thing we can do that we did in the first set of slides that we looked at is we can substitute the area, the incremental area, to be a combination of the incremental height and the width. And this is important because then we can integrate with respect to h instead of a. We're only really interested in h because it's really the direction of the variation of the pressure. So we take our definition, our incremental area is equal to our fixed width. We're assuming that the container has a fixed width, w, times by the incremental height, dh. And this is what we have to solve. So we've taken w and gamma outside of the integral. They're constant. And we only have to integrate with respect to h. So at this stage, it won't be obvious, but I can draw a link, a comparison between a centroid and this expression. So it's just the vertical height, and it's being integrated. So we integrate it to get h squared over 2, and this becomes an expression for the average force that's acting on that wall. So we can, for the purpose of analysis, we can split up these terms. So gamma w h squared over 2, we can rewrite that as gamma hw, which is the area, times h over 2. Another way to rewrite that is gamma area times hcg, which is this distance, h over 2. And if we recognize that the pressure is a force per unit area, we can say that the pressure at the center of gravity is the specific weight times the height, the distance to the center of gravity. This is a first important result that we have in the textbook, and we're going to be using in an example later, that the pressure at the centroid of the wall is simply equal to the specific weight times that distance to the centroid, and then the force is simply that pressure times the area. So we're okay with that. That's something that we can accept. Like I said, it gets a bit more complicated when we calculate the moments, but for now, let's put that into practice. Okay, so this is a question that's taken from your tutorial sheet. So this one's for free if you like. This is, I think, tutorial sheet question 5. Tutorial sheet 2, question 5. And it's saying, find the hydrostatic force per unit width on the rectangular gate AB. And using what we've just defined on the previous slide, we say that our average force, the hydrostatic force, is the pressure at the center times the area of the gate. And in order to find the pressure, we need to go the distance down to the center of this gate. So the first thing we need to do, or if you like, the most important thing we need to do is identify the centroid of that rectangular gate. Yeah? Yeah, absolutely right. So the centroid of AB is a distance 4 below the surface. So if we want to calculate the pressure, at that point, we have to just substitute 4 into our specific weight, which is 1,000 of density of water times gravity. And this gives us the pressure acting at this point. And then simply, if we want to calculate the force, it's that pressure times by the area 2. Now, I think probably the conceptual difficulty in this question is that it asks for the force per unit width. And you're not given the width. And in that's quite common. If you were designing a gate, you might want to know the force per unit width to understand what might be the limitation in the size of the gate. So in this example, we're assuming to start with it has a width of 1, but we have to make sure that the units reflect that we haven't added a width. So it's a force per meter. So this is our force acting on the gate per meter of width. If it was 2 meters, then the total force would be twice that number. Yeah. What's 4? 4 is the, I could have drawn it better. So 4 is the distance from the surface down to the centroid of the rectangular gate. So it's 3 plus half of 2. I added this earlier because I thought it would be useful for you to see one of the questions in your tutorial sheet. Any other questions or comments? Yes? Kilonewtons. Yeah, it might be that might need to be a decimal. Yeah, I think that should be a decimal, not a comma. Okay, so go back to this slide. This is saying that our average force on a submerged vertical wall, we can find that just by calculating the hydrostatic pressure at that point times by the area at that point. What we're going to do now is find the sum of the moments of all of those forces that are increasing as you go vertically down the side of the container. This is a little bit more involved, but it's exactly the same process. So before we showed that if we have our expression for force being the sum of our specific weight, the product of the specific weight and the width times the integral of the height as you go down, then you get this expression for the average force. Now we're going to do the same, except that we're going to times each incremental force by the distance from the surface. So we're going to do the sum of the moments. It's exactly the same expression, but we have times h. So it's going to be h cubed. So we have F times h. So instead of gamma W integral of h, we have gamma double integral of h squared. The process and the justification is exactly the same, except now that we have the extra h, we have h cubed divided by 3. Times by our specific weight gamma and our width w. And so this is, if you like, our answer. And I'm going to highlight this again in the next slide, but already you can see some links to what we had at the beginning, the centroid, the first moment of area, and the second moment of area. You might remember that the second moment of area of a rectangle around an axis was bh cubed divided by 3. And here we have wh cubed divided by 3. So you can start to see where the second moment of area is needed in this analysis. So we can make some observations. If we have our moment being gamma wh cubed over 3, we can relate this to the force. So we have gamma wh cubed over 3, which is our sum of the moments, is equal to the resultant force times the center of pressure, which is the resultant force is the average force, which is this, times the center of pressure. And by relating those two expressions, we can prove that it acts at 2/3 of the distance down from the surface. We cancel the gamma w's, and we're left with an expression that says that the distance hcp is equal to 2/3 of h. And this always holds for a constant density fluid and for a vertical plate immersed in that fluid. Yeah, so the forces on a vertical wall can be summarized by these three terms: the average force, the sum of the forces, and the distance, which is 2/3 of h. And you can see, as I pointed out in the last slide, that actually there's already this clear link between the second moment of area around the axis and what we calculated to be the moment. Now, okay, why did we go through that analysis? It wasn't needed, arguably, to understand the forces on a rectangular plane, but we needed to demonstrate that it's the same if you do it step by step or by using the second moment of area. In the general case, we won't have a rectangular shape. You might have a triangular shape, a circular shape. You might have a random geometry that you need to calculate the force on. So we need to understand the principle that you would use to approach that. And surprise, surprise, you need to use a second moment of area. And this is how we get to this diagram, which is in the book and it's in the condensed notes. And there was already a few comments on the piazza about this. There's a lot going on in this diagram. It's a bit complicated. But hopefully, we can start to see now the elements of what's going on in this diagram and how we would calculate the forces that are acting on an arbitrary plane. So two things have changed in this diagram that make it a lot more complicated. The first one is that it's not horizontal, or it's not vertical, it's inclined. So it's going to have a component of x and a component of y. And the second one is that it's not a shape that we have a reference value for second moment of area. It's an arbitrary shape. So in order to solve this, we need to do two things. We first need to define the inclination of the plane, and that's going to be defined by this new coordinate here, zeta, which is equal to h divided by sine theta. You can use whatever symbol you're comfortable with, but this is just a way to measure the distance along that incline, along the surface of the immersed plane. And the second thing, as was pointed out earlier, is that we now have a more complex area that we would need to do a double integral on. Yeah. No, it's the distance along the slant. So our x and y axis are, our x is in the direction of the horizontal and our y is in the direction of the vertical. We have this, I've taken this from the book, and this is why I introduced h as being the variation in height. And this, whatever you want to call it, zeta is our, it's not zeta, it's something else, but is our variation along the slant. So this diagram is just showing you both a side view and a plan view. So that's why it's a bit confusing. So up to here, this is just showing you the side view of that surface, and then here it's showing you the view down. Okay? So we need to have both the side view to understand the variation of forces in the vertical direction, and we need the plan view to understand how that geometry is arranged so that we can calculate the center of its gravity. So this diagram is taken straight from the textbook. There's more discussion and explanation about how they set up and approach that problem there, but it's the full analysis. So in the textbook, they're making sure that you can apply this approach to an arbitrary problem. In our analysis, we're only really we're focusing on simple shapes to get the understanding clearer, and then you're going to have the chance in the next couple of weeks to apply this to slightly more complicated examples to see how it varies. In the textbook and in the supporting revision guide, there's a load of questions that look at how forces vary on planes and also curved surfaces. Curved surfaces is another step in complexity. You have to integrate again in the direction of the curvature. But the basic principles are always the same. Yeah, so we have our height, we have our distance along the plane, and we change a little bit. We make a substitution so that our coordinate system is now going in terms of the distance along the inclined plane. Okay. So the main thing I want to say from this slide is that regardless of your coordinate system, you get exactly the same result. A more complex shape needs a more complex coordinate system, but the same principles apply. One thing that is a bit different in this case is that we usually look at, because in the case of a rectangular plate, it's very clear that we have a top and a bottom or a side in order to start our analysis from. It's less obvious when you have an arbitrary shape. So instead of starting, so in a triangle you could start from the base, in a circle arguably you could start from the radius. But in an arbitrary shape, rather than start from one of the extremities, which may not make sense, you generally start from the center of the gravity. Okay, so you start from the center of gravity, which you can always get for an arbitrary shape, and then you do your analysis for second moment of area from that point. So in this slide, which is again in the supporting video, this is taken from the asynchronous video explaining second moment of area that I uploaded at the beginning of the week. As well as calculating the second moment of area of a shape from the bottom, we now calculate it from its center. And you might remember that the second moment of area around the x-axis, when it was calculated from the bottom of the shape, was equal to BL cubed divided by 3. If you then compute the same quantity calculated from its centroid, it's BL cubed divided by 12. Okay, it has less of an inertia because the distance to the size of the shape is smaller. So it's going to be divided by a bigger amount, so it's going to be overall, it's going to be smaller. One thing to point out, second moments of area, their units are meters to the power 4, right? That doesn't make a whole lot of sense physically, but important to know, it's 4 distances times together. You've got 3 times the length and 1 times the width. So when you're writing and calculating second moment of area, make sure that you use the right units. It's meters to the power 4. Okay, covered a lot of ground there, and I entirely appreciate that quite a lot of that's pretty tricky. Is there any questions that you want me to try and go through or try and respond to now before we finish? Or do you want to start to try and do that through the medium of examples, which I always think is the best way? So, anyone got any thoughts, questions, comments? Yeah, there's one. Guys, quieten down, please, just so we can hear the question. Thanks. Right. So the question is, and I think you mean in the context of this module, so the question was, in the context of this module, will you be required to calculate second moment of area? So you're going to be, so spoiler alert, you'll be asked to do something simple in the coursework. But in the exam, you wouldn't be required to do that because you won't have the reference values available, perhaps. In the real world, in engineering, yeah, of course, you have to calculate your own values of second moment of area. But in an exam, we're not looking to test mathematical complexity. In an exam, we're always looking to test principles. So yes, you're going to have to do this in the coursework. No, you're not going to have to do it in the exam. Yep. In an exam? Yeah, so the exam's just the last couple of days, we finalized your exam. So I now know everything that's in the exam. So listen for the hints. And I now know everything that's in the formula sheet. So yeah, I'll upload an exam. I'll upload a copy of the formula sheet so that you can see what you'll have to hand in the exam. Any other questions? Yeah, there's a question at the back. Sorry, could you say that again? I couldn't hear you. Okay, yeah. So it's quite a confusing diagram because they've tried to combine both, but the side view is this. So you imagine you've got a tank of liquid and you've got a plane on its side and you're looking at its side. And the plan view is this. So then you're switching your view to look face on to that plane and you're seeing that it's not rectangular, it's an arbitrary shape. Yep. Yeah, that's a really good question. So the question was in a real world scenario, how would this plate stay in equilibrium? Because if there's a center of pressure here, there needs to be some force acting in order to keep it in that position. And that's what is represented here, right? So there's some examples I've seen in online and some experiments that you can do with special equipment that show that if you have a surface submerged in water, if you try and support it at its center of gravity, it doesn't stay still, right? If it has a vertical inclination, it doesn't stay still if you support it. If it's horizontal, it will. You can think of like a float in a swimming pool. If you try and support it while it's vertical or inclined at its center of gravity, it won't stay still. So you have to move your center of pressure, your force to the center of pressure in order to balance that motion. Yep, last question then. Yeah. So the question is this the same axes as in this picture? I think on the diagram it's confusing. They're two different coordinate systems. So if you like, you have a global coordinate system, then you have a coordinate system aligned to the plane. So it's a bit confusing. Okay. Right. What I'd like you to do, because it's very relevant to the coursework and to your tutorial, is have a go at this question from the book. It's a worked example. Okay. So if you go to the book, this question explains how you solve. It's in the book. It works it out. That doesn't mean that it's simple. So have a go, read through it, and next week I'll post a video that takes you through the solution. And if you understand that, then I think you're going to be okay for the coursework. Okay, that's it. Thank you very much. See you next week.